This is AP Calculus, Lesson 5-9. We are still on Standard M. Where are we in our unit? We are right at the end. This is the last lesson for the unit before we move on to the self-checks. As a note, tonight you don't have self-checks for homework just because all of the self-check solutions are going to be recorded anyway, so if you don't finish in class, you'll have homework. Alright, so this is the setup. Go ahead and copy it down. Alright, now that you have me unpaused, let's go ahead and solve these. So I need to just review all four of these in terms of the graphical and the analytic way of solving them. So let's first solve this analytically, and then we'll solve it graphically. So solving this analytically just with the equation, this is going to become 4x to the power of 1 evaluated between 0 and 3, and that is going to turn into subbing in 3 times 4 is 12, and then 0 is going to be minus 0, and my final answer is, well, that was a weird arrow, is 12. So I want to teach us a little trick for doing constant functions, and you might have already noticed this. You can just do, if this is A, we say if that's A and that's B, then your general formula is B minus A times whatever your function is, and then we'll put, it's a constant, so it's a number there. So it's really, if I use this formula, B minus A, that's 3 minus 0, so it's 3 times the number, 3 times 4, and I get 12. That's it's not that much of a shortcut, but it does save a little bit of time on the AP test. Just do the end minus the start times whatever the number is. That's only for constant when you don't have any variable in here. All right, let's go on to the graphical part of this. So the constant function 4 dx, what is that going to look like? Let's go ahead and grab our line tool here. So that's just going to be a flat line right here. Oh man, jumped there at the end. Let's grab that. There, I'm satisfied with that line. And we are going between 0 and 3, so 0 is here, 3, make our line. Right there, we're trying to find this area. This area right here. Alright, so this is just a rectangle, 3 by 4, 3 times 4 is 12. Has an area of 12, it's above the x-axis, therefore it's positive. Perfect. Moving on. We have a linear function. So a linear function is just some x, not raised to any power. How do I solve that analytically? There's no trick for this one. I mean, this one you can kind of see in your head because it is so simple. But this is going to be x squared raised to the power, divide down. And that's evaluation bar 0 to 3. And subbing in 3 squared is 9. Half of 9 is, I'm just going to say 9 halves. Leave it as a fraction. 9 halves. Subbing in 0, I get 0. And my final answer is 9 halves. If you don't like a fraction, that's about 4.5. Both of those would be fine. What does that look like on a graph? So this is just 1x plus 0. So plus 0, that means the y-intercept is here. And it goes right one, up one. So here, it's going to be roughly, my points might be off a little bit. And if I made my line, it would look like that. And so now that we have our line, we need to go ahead and connect it to the x-axis, just like we did in the homework last night. And what is the area that we're trying to solve? Let's go ahead and shade that in. So we're trying to find this area, and of course I always love to make that into a rectangle, so I can't make an error. This rectangle is a 3 by 3, which is 9, and then it's half because it's directly cut in half with a triangle, and that again is 9 halves. The same answer that we got up here, making sure that they are the same answer. Let's talk about a quadratic. This is just, technically I could give you cubic, anything else. It's just a random example here. If I had this one analytically, and of course you should be pausing me and try to do this on your own. So pause me now. Alright, so you've unpaused me now, so what is this going to be? It's going to be x to the power of 3 and divide down, so a third. And that's evaluation bar, evaluated between 0 and 3. And that is going to turn into, the 0 is going to be nothing, so it's just 3 cubed. It's 27 divided by 3, and that's going to be 9. Minus 0, but I'm just going to say 9. Just skipping a step there. I know 0 plugged in is 0. What does a quadratic look like? It's a U shape. My scale here on my y-axis is a little bit off, but I think we can kind of go with it. So 1, 1, 2, 4, 3, 9. Ooh, this is going to look a little bit off. It should be a parabola. It should look, I'm going to try my best to make it, it should be a U shape. I tried. Yeah, but this is supposed to be a curve. If you guys can make it more curvy than I can, that would be great. It's some U shape, and it should be nice and flat here at the 0. And then how do I do this graphically? So I'm going to go ahead and draw my line at 3. It goes from 0 to 3. How to find the area of that? It looks like a triangle in my drawing, but it's not. This is a curve, and we don't know how to find the shape. This is not any shape that we know of. I mean, there is a complicated way of finding it, but you can't really do this one graphically. So let's go ahead and make a note here. So graphically, graph, my A and G are not going to graphically, make a sad face, can't do it. Sorry. So let's talk about piecewise. So I haven't really given us very much information for how to solve this one, but the main thing to take away here is you just find the area in between the curves. So you're really finding this area here, and this area down here, and this area up here. That's the main thing to take into account. And if I'm finding between 0 and 3, I add up all 3 of these areas. Keep in mind, let's go ahead and write a giant plus here, maybe a bunch of pluses. Yeah, so this one is positive, this one is negative, and this one is positive. Just keep that in mind when you're adding them up. That's piecewise. And if I added that all of these 3 together, that would become net change. So you can make a note here on the side too if you want. You can say that net change, just a vocab word that they'll sometimes use on the AP exam. That is the total area. Just think of that as like total area in terms of this graph. Add up all 3 of these, that is the net change. All right, perfect. All right, so moving to the next slide, we have the definite integral rules. This is the new stuff, and this is going to be the final slide. So go ahead and do the setup. Pause me. All right, you've unpaused me. So this first one is pretty straightforward. So you start and end at the same point, and I'll make that note on the side. But when I start and end at the same point, that's like a 0th of a sliver. Like I didn't even move. So that is 0. Oh, wrong color. Let's switch here. That is 0. Actually, I do like the color change. I'm gonna keep that, but I'm gonna change it to red. 0. And we can make a note here that you start and end at the same point, Perfect. All right, let's look at our second rule. So integral from a to b, assume a and b are not the same point, so you're not talking about rule 1. And what is happening here? We just have a k in front of here. And this is going to turn into, changing back to red, it's going to turn into k times the integral from a to b of your function f of x dx. And you can see what the difference is here. All we did was we pulled the k outside. So if my k, think of this as a number, not a variable like x or 3x squared, but like a number, just 2, 5, pi, e, some number. If it's a number, you can pull it out, and we'll write that down too. If multiplying by a, oh, I don't know what's going on there, by a, instead of saying number, it's really a constant. So we'll say a constant, comma, pull out of integral. And you can put it back in too. I mean, you can go backwards and forwards, but generally speaking, you want to pull it out. Perfect. So we should also note that this k here, I said it, but I didn't write down that k is a constant. Perfect. All right, so moving on to number 3. So I have an integral from a to b of 2 functions adding together or subtracting together. I could have just wrote adding and then done this and then done another one for subtracting. But that's really the same rule. So adding or subtracting, that's one or the other, not both, usually. So what is this going to turn into? You just apply the distributive rule. So you're basically saying, I'm going to change colors here to green. So you're basically saying take this integral and distribute it to this function and distribute it to this function. So the way that I do that is I say this is going to be the integral from a to b of the first one, f of x dx. And then I'm going to add if it was adding, or subtract if it was subtracting. So plus or minus, and then do the second integral from a to b. It's the same integral of, whoa, what happened there? My g is weird. G of x dx. So that's kind of like the distributive property, I guess. All right. So rule number 4. It looks like a normal function, but if you take a look over here, it's from b to a instead of a to b. So what this is going to happen, or what's going to happen, I'm going to flip these. I'm going to say now this is going to turn into the integral from a to b. What happens if I switch these, just flip-flop them? If I flip-flop them, then that's going to turn into negative. Actually, I could leave the negative on the inside, but I'm going to use rule 2, and I'm going to leave that negative on the outside. Negative, well, that's kind of a big negative, negative a to b of that same function, f of x dx. So switch the start and the end with each other, and then it becomes a negative. And that kind of makes sense if you think about it graphically. This one is saying I'm going to go backwards. I'm going backwards from b to a. So if I go forwards, now I'm going negative. I'm flip-flopping it. All right, so, and then 5. This is going to be the one that trips up most of us for the homework. So if you're getting messed up over and over again, and it's a really hard one, it's probably rule 5. I just took a look at the homework, and there are 3 of them that are kind of hard using rule 5. Keep in mind that you can subtract these as well if you're going the other way around for this problem. I'll talk about that really briefly in a sec, but the main thing here is if I'm going from A to C, and then from that same C to B, I'm really saying I'm going all the way from A to B. C would be like our suspect point from our last lesson. So what I'm really saying is I'm actually going from A to B. C is included in here of that same function. These both had to be the same function, f of x. F of x dx. And what I mean by you can go in reverse of that is I can say, well, I can subtract one of these. So if I subtract c to b of f of x and move it to this side, and I'm going to, I would like to write it here, but I think that's going to mess up the notes. But I can subtract this integral from both sides, and this rule still holds up. This should really be an equal sign, I guess. So just keep in mind you can subtract an interval from each other, or from the bigger interval to get the smaller interval. All right, that is, oh, maybe I was going to end, but we should write the notes here. This is distribution, can't speak, distribution. And this one was going from start to end, so you start and end. These guys, you go back and forth, so you switch those, and that implies negative. Whoa, my G's are weird today. Negative. And finally, I guess it's really the 2 parts add to the whole. And graphically what's happening is it's saying, like, if I take the distance between here and here, and the distance between here and here, and add them up, it's the same as the distance between, or the same area as here to here. All right, let's undo that for the final notes. And that's saying like the sum of 2, it is smaller, so I'm going to say smaller parts. Smaller parts adds to one big part. All right, and that is all I have for the notes. So go ahead and do your summaries now. Remember that tomorrow we're having 2 self-checks. I will have video solutions for both of those up. Yeah, be ready for that. All right, thanks.